So the next experiment we're going to be looking at is something called the Compton Effect. This is another experiment that showed that particles, or that light, has some particle properties to it. So this was 1923, so this is about 20 years after the Planck's experiment. And so Arthur Compton's another name that you should know. And what he was able to do is demonstrate that those photons, which are basically the particle view of light, that those ones had momentum. Now, do keep in mind, photons don't have any mass, so they're just massless particles of light. So it is a bit odd to think of them as having momentum, and certainly we'll have to use a different equation than the regular momentum equals mass times velocity. But he was able to demonstrate that they have momentum. And because momentum is a particle property, this just gives further validity to this idea that light can be treated then as a particle as well as a wave. And so there's really three experiments that we'll look at basically to show the particle properties of light. So Planck's hypothesis, that was with the blackbody radiation. Einstein's photoelectric effect, which we'll look at next week. And then this Compton effect, which was then the momentum for those ones. Now do keep in mind, we also still have then the proof that light must also be treated as a wave. And so that's that diffraction experiment by Thomas Young. And so we have evidence for both wave and particle properties then for light. Now this does work out nicely mathematically, and we have a fairly consistent theory of that. But conceptually, it shouldn't be possible to have something that can be both a wave and a particle, because those two are actually somewhat incompatible in terms of their overall properties. And so there are some problems still with this theory, but currently it's the best one that we have, and so we run with it. What Compton did, and so just for the experimental design, is he took high energy X-rays, and so these were basically high frequency, very, very short wavelength light waves, and he shot them at a thin metal target. And when he shot them at a target, two things came out. One, we had this scattered electron, and then we had then another X-ray coming out. So still fairly high frequency, but a lower frequency than the incident one. And so when you looked at just the overall energy of this one here, if you take the energy of this incident photon, that was a combination of the energy of this electron that came out, plus then the energy of the wave here. Now, because then this photon lost some energy to this electron, he also thought then that this should also then be losing some momentum to there. And when he looked at the overall momentum, and remember that momentum is always conserved, he could only come up with then a conservation of momentum if some amount of momentum then was assigned to each of the X-ray photons. So we're going to have two equations that we're dealing with this year. One is going to be one for the scattering angle, and then a second one for the momentum. So we'll do the scattering angle first. Now this equation is actually fairly complicated to come up with. So it is based on the conservation of energy and the law of momentum. But because these are moving very fast, you do also have to get some relativistic effects in there as well. So we're not going to be looking at the derivation of this one. It is on your formula sheet, and so we'll just use it as a value there. Now when you're going through this one here, the change in wavelength here, that's going to be your scattered wavelength minus your incident wavelength. So final, so your longest one, minus initial, which will be shorter. So it should always give you a positive value because this scattered wavelength will have a longer wavelength, which is lower energy, than your incident photon, which has a higher energy and a shorter wavelength. This M here, that's this electron, so the mass of the electron. So it's on your formula sheet, 9.11 times 10 to the negative 31. The angle here, now we do have an angle for the electron and for the photon. This angle in this equation is for the photon, so it'll be your scattering angle. Now in your questions, you'll only have one angle given, so that'll be fairly straightforward, but it is for the scattered photon angle. H is Planck's constant. Now this one here, because we're dealing with the mass, Planck's constant, we do have to always use the 6.63 times 10 to the negative 34 in joules times seconds. We can't use electron volts for this one because we won't get a cancellation with our mass units there. So do watch that for Planck's constant. We always have to be using this version of that one for this equation. And the last one, C, the speed of light, 3 times 10 to the 8 meters per second. That one's on your formula sheet then as well. The second equation we look at then is for the momentum of those photons. Now obviously we can't use just P equals mv because those photons are massless, and so that would just give us zero momentum. In the time between Planck's work and Compton's work, Einstein had done a fair bit of work with mass energy equivalence. He came up with this fairly famous equation, E equals mc squared. And what this shows us is that for any mass that we have, we can write that mass in terms of an equivalent energy. So if we multiply a mass by the speed of light squared, that'll give us then the corresponding amount of energy for that particular mass. And so we can look at those two then as related. And so what Compton was able to show is that if you substitute this mass with an E over c squared, you will get a momentum, then that for his scattering experiment will make momentum then conserved overall. And so if you substitute that m with E over c squared, now this is only valid for massless particles. Please don't try to do this with other types of particles. But this turns out to be valid for these photons. Take the E over c squared times the velocity. Now, because it's an X-ray, your velocity is just that speed of light again. And so we get one of those canceling out. And so then we get P equals E over c. So for a massless particle, the momentum is the energy over the speed of light squared. Please do not ever put this in for any particles with mass. Particles with mass do not have a velocity that's equal to the speed of light. They're always going to be slower, and so this isn't going to be a valid equation for those. So just make sure that you're only using this equation for photons. P is the momentum, very specifically of a photon. I is the energy of the photon, speed of light. The relationship then we can also describe in terms of the wavelength of a photon, and that's just using our ideal wave equation. And so the frequency then is going to be c over the wavelength, or E equals hf. So if I put E for hf, I get P equals hf over c, and so it's one other way we can describe then the momentum in terms of a frequency. And then we can put in that c over wavelength for our frequency, and we'll get h over wavelength then when everything cancels out, also for our wavelength. So we have a couple other ways. This one's on your formula sheet. This one's not, but you can derive it fairly easily using then that ideal wave equation. But those are other ways then you can express the momentum of a photon in terms of either its frequency or its wavelength. And again, make sure that you're using those just for photons. The E equals 1/2 mv squared, that's only for massive particles. So if we're looking for the energy of a photon, we have to use that hf equation. And P equals mv, that's again only for massive ones. So make sure you're not using those for photons. Likewise, make sure that you're not using these photon equations for particles with mass. Now your calculations for these ones are going to be fairly straightforward. Again, just make sure that you know whether you're dealing with a photon or a particle with mass. In this case, of course, we have a photon. And so the momentum of a photon, we'll just use that h over f. Now, if we're given an energy, we can use the E over c. If we're given a frequency, we can use that equation. If we're given a wavelength, h over f is what you'll want to be using then. And so don't forget, we do have to be using then that 6.63 for these ones here, just because we're going to be in meters here. So 6.63 times 10 to the negative 34, that'll be Planck's constant. And then our wavelength then, 625. Now make sure you're putting that into meters, so put in that times 10 to the negative 9, joules times seconds. And that'll give us then a wavelength, or a momentum of 1.06 times 10 to the negative 27. Now that will be in kilograms meters per second, and that'll be then our final answer. That's typically what we want to put our momentum units then in. If we look at this one here, just in terms of our units, and so this is a bit of an aside, but if we put this in terms of our unit, a joule, so what we have is joules times seconds over meters. But don't forget, a joule is a kilogram times meters squared over seconds squared. And then if we're multiplying that by that seconds over meters, which is those other two there, we see then that one of those meters cancels out, one of those seconds cancels out, and we're left with kilograms meters over seconds. So as long as you're in joules here and meters here, these units will always work out to the momentum units that we would expect. So for the next one here, we're going to be looking at the scattered photons. And so we're going to be using the scattering equation for this. So we have the change in wavelength is equal to h over mc. And that'll be then 1 minus the cosine of the scattering angle. And we'll do these always in degrees for those scattering angles. Now my change in wavelength is going to be the final one, so that's the scattered one minus the incident wavelength. And so make sure it's always scattered minus incident. This always needs to be a positive value, so that scattered one is going to be the longer wavelength. And that'll be h over mc. Don't forget, this h has to be the 6.63 times 10 to the negative 34 for our units to work out. And then we'll get, of course, 1 minus the scattering angle in degrees. Now I will for this one here, I'm just given the energy of the initial one, or the incident photon, and so I'm going to have to change that then to a wavelength. And so I do have that energy equals hc over wavelength equation, and that's just Planck's equation in terms of the wavelength. And so my wavelength here will be hc over my energy. Now in this case, I am given an energy in electron volts. So here it is going to be convenient to use this in electron volts and then the 4.14 times 10 to the negative 15 for Planck's constant. And so just watch those energy units. If your energy is given in electron volts, that's a convenient way to go. You could also change the energy to joules and then use the 6.63. But it's a bit easier just to use the change for Planck's constant. And so we have 4.14 times 10 to the negative 15. And that'll be in eV times seconds. I will multiply that by the speed of light. So it'll be that 3 times 10 to the 8. And that'll of course be in meters per second. And all of that then will be divided by that 20,000. Now that's in kilo electron volts, so we do want to put that just into straight electron volts. And so then we get that 20,000 showing up there. Your units will cancel out. I get EV over EV, my seconds, and so I'm left with a wavelength in meters, which is what I am expecting. And so my wavelength then, I will just work out to be 6.21 times 10 to the negative 11. Of course, in meters. So then I can rearrange this equation. My scattered wavelength, which is what I'm looking for. Now when I'm going to take this incident wavelength, I'm going to move it to the other side. It becomes positive. So I'll get that 6.21 times 10 to the negative 11. That'll be in meters, and that'll be now on the other side of the equation as a positive. I'll add to that here. Now here I'm going to use that 6.63 times 10 to the negative 34. That'll be in joules times seconds. I'm going to divide that by the mass of the electron, so 9.11 times 10 to the negative 31. And that'll be on your formula sheet, so you can just look that one up fairly easily. And of course, 3 times 10 to the 8. That'll be in meters per second for the speed of light. And then I'll multiply all of that by 1 minus the cosine of that 35.7 degree scattering angle. And make sure your calculator is in degree mode then for those ones. So when I add those two together, I get my 6.21, I'll just do this in 2 steps, times 10 to the negative 11. This whole one in here, when I multiply that one out, I'll get 4.55. And again, do keep that whole number in your calculator, times 10 to the negative 13. Now that one will also end out in meters. This 1 minus cos 35.7, that will not have any units. My joules, being a kilogram meter per second squared, my kilograms are going to cancel out. The 2 seconds will cancel out, and I'll be left just within a unit in meters. You should be able to see those units canceling out. But both of these then will be in meters, and so then of course I can add those two together. And so when I do add those two together, I do get that slight change. So 6.26 times 10 to the negative 11 meters. Now it is still a very, very small wavelength because it's in the X-ray region of the spectrum, so make sure that those ones are quite small. And make sure that you're then adding on that initial incident wave to those ones as well. But that'll give you then the longer wave of the scattered X-ray.